Hello everyone, welcome to this talk. My name is Denis Magda, and really brief, what we are going to explore today. We are going to talk about the in-memory computing essentials. Today the market is overwhelmed with a variety of different memory computing technologies. Let it be an in-memory cache or in-memory database. All of those technologies and products provide you with various capabilities and benefits. But also there is something that unites all of them, something that is quite universal and belongs to every type of the cache or every type of an in-memory database. And those universal capabilities I'm naming as the essentials. And the next 30 minutes we are going quickly overview all of those essentials that you should keep in mind if you are planning to deploy or design applications for kind of your data intensive applications that will be running on an in-memory database or on an in-memory cache. Alright, let's move on. A little bit about myself. My name is again Denis Magda, and presently I've been working with distributed in-memory systems for more than 5 years. I'm gaining practical experience by contributing to Apache Ignite project, which is essentially an in-memory database or a cache. And also I'm running developer relations group at GridGain, and GridGain is the company that originally donated Apache Ignite to the Apache Software Foundation. Before distributed in-memory systems and before Ignite and GridGain, I was involved for many years in the development of JDK and JVM. I used to work for Oracle and Sun Microsystems. In particular, my zone of interest was JDK and JVMs for embedded devices and mobile devices. And also my professional career started at Sun Microsystems when I was advocating various Sun technologies, including Java, NetBeans, Solaris. We were running local Java groups and building some fancy projects. Alright, how does our agenda look like today? First thing first, we need to start with the introduction. I will try to answer the question why in-memory computing matters, why do we really have so many distributed in-memory caches and databases. Then I will give a brief overview of Apache Ignite, because that's not only the project I'm contributing to, but also I'm going to use Apache Ignite to demonstrate all those essential capabilities in practice. And finally, we will quickly go through the list of the essentials. We will start with data partitioning, that's the essential of essentials, and then we will carry on with the review of affinity collocation and collocated computations. Alright, but first thing first, why in-memory computing? And the answer is trivial, it's simple, it's all about speed and scale. So where does the scale come from? Let's imagine that you have an application, and that application is connected to your in-memory database or your in-memory cache. And presently, it's more than enough to have 3 nodes in your distributed in-memory database. But then the data volume that your application needs to process might grow, or you might need to kind of handle a much larger data load, or like a workload. And what do you do in return? How do you tackle this problem? With distributed in-memory systems, all you need to do is to scale your cluster horizontally. For instance, if you need 5 nodes to handle all these requests or to keep more data set, just scale your cluster. If you need more nodes, just keep doing this as soon as you're comfortable with the current cluster configuration. Alright, and where does the speed come from? We all understand that memory is much faster than disk. But how much, how big is the difference? I always find this table handy. So what this table shows, in the first column the table lists some of the most frequent events our CPUs have to complete, some of the most frequent operations. And in the second column we have the actual latency, the actual time it takes for the CPU to complete any of the operations to the left in the first column. All those actual latencies are in nanoseconds, microseconds, and milliseconds, which might be hard for us to comprehend, like how vast is the difference. That's why in the third column we have so-called scaled latency. What the author of this table did, he actually assumed that if to suppose that 4 nanoseconds, that's the first row, 1 CPU cycle, is equal to 1 second, then we will apply the same formula and we will come up with this scaled latency that is much easier to comprehend in our human universe, because we can understand the difference between seconds, minutes, or days. And right now, if you pay attention to some of the rows, and if you compare the main memory access to disk access, you can see how startling the difference is in terms of the latency time. Yes, if to look at the actual latency, that's just the difference between nanoseconds or microseconds or milliseconds. But in our universe, if to believe to our scaled latency, that's like the difference between minutes and days. And that's why in-memory computing software like caches or databases are becoming so popular nowadays, and that's why we are deploying them together with our classical and legacy databases. That's all about speed, and the speed comes from this much faster data processing, much better latencies, and from the scalability. Those in-memory systems are designed to be scalable, horizontally scalable from the very beginning. Okay? The next topic, Apache Ignite. As I mentioned, Apache Ignite is going to be used for the exercises and for some of the code samples, but nevertheless, all these essential capabilities, as I stated, are universal. And even you don't need to use Ignite to benefit from those capabilities. But you can use any other solution, such as Redis, I don't know, MemSQL, VoltDB, Hazelcast, etc. And still those essentials will be helpful for you because they will help you to and guide you in your new design phase when you will be building your application that interacts with in-memory system. But anyway, let's go back to Apache Ignite. So in short, if to give you a 2 minutes introduction, Apache Ignite is, if to believe to the website, is an in-memory computing platform. It goes with a variety of different capabilities, but in fact, the two primary features of Ignite is its multi-tier distributed storage and a variety of different APIs that can help you to process the data stored in that distributed storage. When it comes to the storage, Ignite can keep data in memory by definition, that's the memory platform. And also Ignite can persist your records to disk. When it comes to the persistence, you have two options. Ignite can store your records in an external database, or it can keep the records in its own disk storage. Okay? And on top of this distributed storage engine, Ignite provides a set of APIs. You can interact with your data stored in Ignite using SQL, key value, transactions, compute. You can run your machine learning models and do many more. Everything you see in the middle, in red, is available in open source. It's provided by Ignite. And to the left and to the right of the screen, you have features that are in the blue box. Those are available from GridGain for those who would like to use an enterprise feature. And an obvious question might be, alright, those are features, but tell me how Ignite is being actually used. What's the purpose of Ignite? And there are many combinations, there are many deployment configurations of Ignite, but I would define two primary ones. First one is Ignite, as other in-memory caches, is used as a cache. Basically, you might have some performance bottlenecks with your applications, or you just need to offload your relational database, and you basically go ahead and deploy Ignite in the middle, like right in the middle, in between your applications and your database. And how Ignite is different, let's say, from classical caches, if you deploy it as a cache. Ignite as a cache provides you with SQL APIs. You can query your data with SQL without any limitations. You can transact on your data, or even you can create Java compute tasks, different Java calculations, and get them executed right on the server nodes. That's, for instance, how Ignite is different, let's say, from Redis as a cache or Memcached as a cache. Another big use case of Ignite is Ignite as a database. From the APIs and capabilities standpoint, you're getting the same access patterns. You can query with SQL, you can transact on your data, you can run machine learning models, calculations. But what's different here is the persistence tier. In the caching use case, usually you have a primary database that keeps the golden copy of your records, while here Ignite can persist all your data, all your indexes in its own native persistence. That's what's shown on this diagram. And as for the let's say project popularity, it's not as famous as Apache Spark or Apache Hadoop, but still it's it's one of the top 5 projects of the Apache Software Foundation, and we have more than 350 top level projects. And also this project is being used by kind of a myriad of well-known companies. Alright, that was the introduction, and before we proceed with the deep dive of the data partitioning, our first essential capability that belongs and characterizes all the memory systems, let me quickly show you how to start our first Ignite memory cluster on our local laptops, and how we can load that cluster with some data, and then to show you how basically we can proceed further. Alright, I'm for a moment I'm stop screen sharing my slides, because right now I need to go to the terminal window. Okay. What I've done before that, I've downloaded Apache Ignite from the website, and right now I'm going to use this script that is bundled in the Ignite distribution to start my first Ignite node on my laptop. Alright, I hit the enter button, and here is what I see. This message says that my first server node is up and running, and that's how many CPUs are available, and that's how much data is allowed to use on my laptop. But we are talking about distributed memory systems, that's why we need to start another node. I'm opening another tab window, and here is I'm executing the identical command. And once this node process gets started, it will be able to auto-discover the other node, and that's how they will form a single cluster. Wonderful. You see, this message suggests that right now we have a 2-node cluster, and and my memory size doubled. So actually that's what being given by default, but you can always configure how much memory space you wanna give for Ignite needs. And also throughout this presentation I'm going to run some SQL queries after we review data partitioning topic. That's why I'm going to use this command line tool, web console. So here is I already have the instance running, and here is I can see that I have 2 my nodes running. That's on my local laptop. I have just started them like 1 minute ago, like and 52 seconds ago. And if I scroll down below, I can say that the cluster is empty. There is no any data yet. And just in probably 5 minutes, once we figure out what the data partitioning is and how it applies to distributed memory systems, we will start building some real application. Okay, jumping back to my slides. And now data partitioning. As I mentioned, for me data partitioning is the essential of essentials, the most basic thing, the most fundamental thing that characterizes not only in memory systems but distributed databases in general. And many of you might be familiar with partitioning under a different name, sharding, but sharding and partitioning is all the same. So let's start from the beginning. In the relational world, we have relational databases that keep all the records in a single instance, usually on a single machine. And the goal of the partitioning is to take all of your records, ultimate goal, and to distribute them across the cluster of your nodes. That's the goal. And today I'm going to use the world database schema. We are going to create and preload the data for the countries and a snapshot of the countries, cities with populations, and also what are the country languages, what are the languages every country speaks. That will be shown in a minute. And right now let's dive into the partitioning details. Partitioning is just one of the algorithms, right? And let's say that I or you as an application developer decided to create country table, like the one to the left. Once you execute this command, Ignite or any other distributed SQL in-memory database will create this country table for you, and then that country table will be split into a fixed number of partitions. You will have partition 0, 1, 2, then partition 3, 5, up to, let's say, some maximum number. In Ignite, by default, we have 1024 partition. Some other distributed in-memory systems might have a different number, and that number is always configurable. Alright, that table is created, and then all those partitions will be spread across your current cluster. So let's say that partition 0 and partition 1024 will go to the first node, and the rest of the partitions will be distributed across the other nodes. And all of that happens automatically in background. All you need to do is just to create this table, and then Ignite internally uses this partitioning algorithm to split it into the partitions and distribute across your cluster nodes. And then once the table is created, the next obvious goal is just let's load some records. And for instance, here is I'm trying to insert the record of the United States, country United States. What happens internally? How does the partitioning algorithm handle this? First of all, it will take the value of the primary key, and it will use a special hash function to translate this key to one of the partitions. And once the partition is known, your application will be connected to one of the cluster nodes that keeps the primary copy, that should keep the primary copy of this record, and that record will be placed on that node, on that specific partition. And we can probably, let's imagine that in case of this record, the primary key is the column code, and it's equal to USA, and we might imagine that USA is translated to the partition 5, and right now that partition is located on the third node, and basically that record will be placed right on that node. Simple, right? Okay, so right now that's the time for the exercise for me. And for you, you can see what we can do with our cluster. Just as a summary, we already have two node cluster running, and right now I want to connect to this cluster using SQL line tool. That's a command line Java tool, and I will be using a JDBC driver of Ignite. I'm connecting to my local cluster. Alright, I could connect, and next I want to run this query without, let's say, this proceeding. Actually, what this query does, it executes all the commands from this file. Okay, probably I need to execute it. No, that's a different one. Yep, we need to execute this one. Yeah, that's a different one. We are loading that from this file. I will show you how that file looks like. While the loading takes place, that's the file. I'm creating country table, city table, country language, and then loading all the data. Simple. Okay, the tables are loaded. Let me confirm that. Okay, I have these three tables defined, and if I jump back to the monitoring tool, I can see, yep, all these tables were created. That's how many records we have. And what's of our interest for now, for this chapter of the presentation, is how the data was distributed among the partitions. Okay, I'm doing this. I'm selecting, let's say, city table, and then I want to see the current partitions distribution. So in fact, what happened? Ignite by default assigned 511 partitions to one of the nodes, and the rest of the partitions were assigned to the other nodes. So here is, let's say, if you want to see which partition is located where, like partition 0 is on that node, and presently in that partition we have 3 records, 3 countries. Then partition 1 is on the other node, we have 2 records there, and you can just observe everything by scrolling down. That's how easy it is. Again, what we've done, I connected to my 2-node cluster, executed this script that basically loaded the table, they created tables, loaded the database, and that's it. All the rest of the magic happened in background. That partitioning algorithm distributed everything evenly, and the same concept actually is available and belongs to every, I bet that every distributed in memory cache or like database or whatever, they support partitioning or sharding internally. Next, the next topic is affinity collocation. So why do we need it? Yes, affinity collocation is one of the first advanced techniques you have to keep in your toolbox when you're designing your data-intensive applications that will be interacting with a distributed in-memory cluster. Why do we need it? So let's take this example. We've just loaded countries and cities, and by default, when you do nothing, all the records will be distributed randomly. That's how the partitioning works. So let's say that in this case we have Canada, the country, located on one node, and France is located on the other node. And what might have happened that some Canadian cities, such as Montreal and Ottawa, are not stored together. They are not stored on the same node where I have the Canada record. And the same is true with the records and the data of France. Marseille is located on the right node, while Paris is located on a different node. And the warning sign suggests that that might be not a big deal for you unless you run complex queries. Queries when you need to join data, let's say, between countries and city tables. Let me elaborate and explicate on that. What happens with this query? My client application connected to the cluster, and right now with this query I want to get the top top 3 most populated cities across countries such as Canada and France. So what happens? This query gets executed. That query arrives in these 2 cluster nodes, and the nodes start executing this query over the local data. But as soon as this come to this joining phase, they will start joining the records, and they will discover that, oh, some data is missing locally, and we need to kind of communicate with each other to shuffle the data, and the data shuffling starts. With this example, like, you will not notice any performance impact. You will not notice any kind of performance degradation, because we are just shuffling 3 records. But imagine if you are running the join over the millions of records, or like thousands of records. Your performance of your cluster can, tumble, like fall down dramatically. And why we should care of that? You remember this table? But that time, initially we were comparing the latency time between the main memory access and disk access. But also keep in mind that all those fancy and nice in-memory systems are connected. All the nodes, clusters, they are interconnected through conventional networking channel, and the network is much slower than disk. It's like the difference between days and years, which means that if suddenly your application starts executing complex queries like SQL with joins, then it will be not surprising if a lot of the data will be shuffled between those nodes, and your performance benefits of your in-memory cluster will fly away. So how can we fix this situation? What can we do about that? You can collocate the data. So generally, what we want to achieve, we want to get such a distribution where all the cities that are located in the same country are stored or grouped together on the same node. It's like right now we want that all the Canadian cities to be stored together, and the same is true for the cities of France. And we, as application developers and architects, all we need to do is to help our in-memory system to understand how this relation is formed. With countries and cities, it's obvious, right? We have the country table. That one has the primary key, which is the code, and we have the city table. And that city table is also uses this country code as part of its primary key. But also then we are saying that for this partitioning mapping, let's say from your primary key, like for the record mapping to the partition to the node, use this affinity key. And what happens when you will be inserting all those cities in the cluster? The partitioning algorithm will be taking the value of the country code, and as long as all the cities that have the same value of the country code, they have the same value of the country code, they will be placed and grouped together and located on the same cluster node. That's it. That's all you need to do. After that, internally, Ignite or any other in-memory database will handle this proper data distribution for you. And once you do this, and if you execute the same query, you see it will be executed locally. All the data is local, and the data will be joined really fast. And you will not have any data shuffling phase. You achieve this. By knowing how your data is related, you'll be able to tap into the affinity collocation. You help Ignite or any other in-memory database to group related data, and now you can run advanced and complex SQL queries. Okay, let's quickly run through an example. We've already have the data loaded, and I've prepared some of the comments for us. So let's execute this simple query. This query returns yet the most populated countries of the world: China, United States, and India. This one is more complex. This one joins country and city tables, and it returns the most populated cities across these countries. So if I execute this command, some syntax issue. Okay, that was some mistake on the tool end. If I execute it, that's supposed to be the answer: Mexico, Russian Federation, United States, Moscow, New York, but that's not the right answer. What happens here? The data is not collocated right now. When Ignite tries to join the data, the nodes do not shuffle the data. So basically, the result set is incorrect. We have to instruct Ignite to enable the data shuffling. I am checking in this flag, and after I execute the same query, we will see the right response. The data, and when this query will be joined, the data will be kind of shuffled between the nodes, but at least it's not the most performant way, but we will be able to get a correct result set. Okay, let's execute it. It takes more time. You see it takes between like 1 second, 2 seconds, and like from milliseconds we jump to like now it executes 10 times slower, right? But that's the right answer: Seoul, St. Paul, and Shanghai. And how do you fix it? Because we want to collocate the data. It's all simple. I'm going back to this script. I have here is my city table, and all I need to do is to define affinity key, which is the country code. And now let me reload this table. The name of the script is different. I'm reloading this table, and right now, just in case, let's refresh the screen. I'm unchecking this button, so right now I know that all the records are collocated, all the cities that belong to the same country are stored together. And when I execute this query, I'm always getting the right result set. And check the execution time. It's just 11 milliseconds versus 1 or 2 seconds. 10 times or 20 times faster. And I achieved this even on my local laptop by collocating records. And all I had to do is just to define that affinity key. Alright? Hope it makes sense. Otherwise, we always have the time to discuss this during the Q&A section. And the final concept, really quick, I will briefly touch point on it, and then you can, explore it in more details, is collocated computations. With affinity collocation, you help the data partitioning algorithm to group and store together related data. But then, let's say you might have some complex operation that is multi-step operation. You probably can get some data first, then you might do some processing, then you're getting another chunk of data, you do some processing, and then you're updating some records, and you're writing the result set. And that back and forth might involve a lot of the data movement between your nodes and your applications. What you can do within memory systems, usually you can create your custom Java task, wrap that logic in the task, and get it scheduled. So what happens on this screen? First of all, at step number 1, your logic will be scheduled for the execution. That logic will arrive to your cluster nodes. It will be executed over the local data. And once every node completes the execution, it will respond to your application, and then your application can reduce all the result sets and decide how to proceed. And that's a tremendous thing, because let's say that if you need to process millions, like thousands of records, and instead of pulling those records from your in-memory cluster to the application, again hitting performance issues, you can wrap your logic into a compute task and get it executed on the cluster. Wonderful, right? If you want to experiment with that, during the Q&A, ask me to share some code samples, and I will share with you the link to the project where I have some of the nice examples that show how you can benefit from the computations. Right? And the summary. Yes, all those in-memory systems promise to be, fast and furious, but in fact, you as an architect or application developer has to keep in mind that you still need to think about details. You need to design your data properly, you need to group your data properly, and then you will be able to run high performance SQL queries with joins, and you can use collocated computations that avoid any data movement over the network. So don't be confused. In memory doesn't mean it means really fast and simple, but also you need to work on that. Alright, and if you want to learn more, check these books. That's what I would recommend everybody if you're interested in distributed memory systems or databases. And alright, right now I'm ready for the questions.